All right, an educative day can't keep unemployment away. Video about it might make you a hit. We are finding the median from a data stream, and here's the problem statement. It's worth reading this one for once. So we want to create a data structure that can store a list of integers that can change in size over time, and find the median from this dynamically growing list in constant time. It's O of 1. So the task is to implement a class, median of stream, which would support the following operations: a constructor that initializes the object of this class, which in turn creates the max and min heap. Okay, so we know there is a max and min heap property in this class, and an insert method that adds an integer to the data structure, okay, to probably either the max or min heap, and a method called find median that finds the median of all elements seen so far. If there are an even number of elements, return the average of the two middle values. So that's what it harkens to what a median is, right? So if you have 4 values, basically, the median is the average of the two middle values in the middle. This example, as usual, should be useful. So in this particular stream of 3 characters, the median is 30 because when they're sorted, 30 is going to be in the middle. It's going to be the middle value. In this case, 30 and 25 will be in the middle, and the average of 30 and 25 is 27.5. And so we can use this quiz to see if we've understood what's going on. What should the output be for this? So this is already sorted, but it's an even number of elements. So we have to take the average of these two together, which should give us 25, I think, because this sums up to 50. And yes, we have understood the problem. Let us go to the solution. We can skip this. We don't really need this. I don't find those things useful in general. So we restate the problem. Naive solution. It's not in constant time, so O of n squared. But there's no point in looking up the naive solution when we can look up the optimized solution. So hold on a bit. So this problem has a clever trick to it. The median of any number distribution is the middle entry in that distribution. And so if it's in the middle, when it's sorted, considering it's sorted, it's the entity in the middle. So we have half of the numbers will be smaller than that entity. The other half is going to be larger. Now, where 2 heaps, the pattern, the overarching pattern comes in is if we know the largest of the smallest numbers, the number smaller than the median, and the smallest of the numbers larger than the median, we can find the median, right? So that's the trick to this whole thing. And we're going to do that with these numbers, with a certain set of values. And we're going to walk through it with this diagram, and it should make sense. So imagine these numbers are coming in, yeah? We're looking through an array, and it contains these numbers in this format. You can see that they're not even sorted. So the first number is 22, and since both heaps are empty, we simply push the negative of the input number to the max heap. So that's one way of doing it, right? The negative. So we put minus 22 into the maximum heap, right? We start with the maximum heap in general. Then 35 is bigger than the top element, so we put it in the minimum heap because we want to keep track. The bigger numbers are this way, the smaller numbers are this way, the median is somewhere here. So for every number that's bigger than the median, and right now we only have 22 in the array, so 22 is the actual median. So any number that is bigger than 22 for now should go in the bigger number pile, and the bigger number pile, we want to know what the smallest number is, so it goes to the minimum heap. That 35 is going to go into the minimum heap, and we know the median, right? It's just the average of these two numbers because we have 2 numbers now in our list. So the average of these 2 numbers is this. Hope that makes sense. So 22 plus 35 is 57, divided by 2 is 28.5. Then we get another number. Next up is 30. Now, it's bigger than the top element in the max heap. So it's bigger than in this smaller numbers pile, is bigger than 22. So we put it on in the minimum heap. Since the length of the max heap is less than the length of the minimum heap, we rebalance the heaps by transferring the top element from the min to the max heap. So the minimum heap should not become bigger than the maximum heap in general for this algorithm to work. And once we do that, odd number of total elements, we have 3 elements in total. So we just pop the top element of the max heap is the median automatically. And that makes sense. The median of these 3 numbers, 22, 35, 30, is going to be 30. So next up is 16. It's less than the top element of max heap. So it's smaller than 30. So we'll put it in the maximum heap. And since it's bigger than the minimum heap, like it's 2 elements ahead in size, we rebalance it by transferring the top from the max heap to the min heap. And you just keep going like that. It's pretty ingenious. But you, at any point in time, you can take the 2 top elements from the heaps, from the 2 heaps, and find your median. You keep going. Same old, same old. Okay? All right? I hope that makes sense. The code will explain a bit more. We can see it in code, right? But this is the formula. This is how to make it happen. And I think the intuition for it is not too bad. All right, so this is the code. Remember, we're supposed to make a class. For the requirements, we have the constructor. Now the maximum heap for the things on the left, the smaller side of the median, and the minimum heap for the numbers on the larger side of the median. And then we have our insert function. We're checking if what's on top is bigger than whatever number we're considering, right? Then we put it in the maximum heap, right? We negate it and put it inside the smaller number pile, like the top. And because it's smaller than the biggest thing there, right? So we just add it to the list of small numbers. Otherwise, we add it to the list of big numbers, right? The minimum heap on the right, maximum heap on the left. And then we say, okay, if the size for the maximum heap, small numbers, is bigger twice, 2 times, like 2 spaces, 2 slots, entries larger than the one for the smaller numbers, we rebalance it. So we take one out of the bigger pile and put it in the smaller pile, just so that things are balanced on both sides. Because again, the median has to be in the middle. It can't be like lopsided. And that's what we're doing here. Otherwise, if the maximum heap, right, if it's smaller, the maximum heap in general should never be smaller than the minimum heap. We just push, we take something from there and put it over here, this other side. So that's what this does, this function does. Then this is the find median, right? The second thing requirement for the problem. So to find the median, all you need to do basically is if they're the same size, right? So it's even, right? They're same number of elements on the left and on the right. We have an even distribution. We have to find the average of the top, and this is how you do that. Divide it by 2. Divide both of them by 2 and just add them. And if they are odd, we just take the one from the max heap and call it a day. And that's all. That's all there is to it. Let's look at the time complexity. That's all there is to this solution. So time complexity is interesting because we're inserting into a heap is a log of n operation, O of log of n. And we do that a number of times. And it essentially, they say it leads to a log of n factorial, which is like, that's super fancy. Sterling's approximation. When they start name dropping people, you know you're getting into weird territory. But it evens out, and you can kind of intuit how this might end up evening out to n log n. But then they also give the amortized time complexity, which, I mean, usually the worst case is what we are looking for anyway. So n log n, I would say, is the insertion. But the median, finding the median will be O of 1, right? Since you're taking something from a heap is an O of 1 operation. So that's going to be O of 1, which fits what they wanted. They wanted it to be a constant time operation. And then the space is the same, no matter what. The same space you need to store the numbers is the same space you need to store the heap. So it's O of 1. It doesn't change or grow as the data size grows. And that's all there is to finding the median for a data string. Thank you for watching.